Welcome to Chemistry 111. I'm Professor Evans. So the test is coming up before you know it. I have it planned for this Thursday at 7 p.m. That's when the most people could make it. Also convenient for another class that's having another exam also Thursday at 7. And so we will be doing an ODM 101. It's the giant lecture hall. They've had a couple like jazz trio things in there. It's not in the science building. It's over in ODM, the next building over. Should have got an email that essentially says this. But that Thursday at 7, going 7 to 9. You have 2 hours to take the exam. You will hopefully not need the whole 2 hours, but I'm there for if, say, you're the type of person who's slow and steady. Bring a pencil, bring a calculator. I don't think you will particularly need a calculator for Chem 111, but I mean, it doesn't hurt to have one. If it helps, bring a page of handwritten notes, front and back. Go ahead. Say, people who are prepared will have it. People who aren't prepared come in like, whoa, crap, I forgot that. Was I allowed to do that? Pretty much, if you're prepared kind of thing. Do you know how to apply this? Do you know how to draw a Lewis structure? Do you know how to determine the electron geometry versus molecular geometry? Do you know the difference between polarity and non-polarity? If you don't know how to do this, the notes aren't going to simply tell you how to do it. So, but if you cannot make it to Thursday, then come find me during the week. I am in my office 11 to 1 on should be every day, unless I'm out like making copies or say heating up my lunch down in the break room downstairs. But I should be in my office more or less around that time. And then I'm in lab 1 to 3 on Tuesday, Wednesday, and Thursday. So you can take it any of those during any of that time period. Just come find me and we'll get that situated. So figure out when's most appropriate for you and come take it this week. You can make it Thursday, great. But if not, get it done this week. I don't want to be hunting down anyone next week. It's this week. That way, hopefully, I can give you the scores back before the 29th, which is the last day to drop the class. By then, you should know, can I make it? Am I going to be just fine? Am I going to pass with B or C? Or is it like, ooh, I failed that test, and I'm not really caught up on the homework. Oof, maybe I'll try again next time. As much as I don't want that to happen to anyone, it's just for your benefit to know how you're doing by that point. Okay, now let's go to Word. Pretty sure we did number 14, but we'll go ahead and do 14 again just to make sure. HClO4 and CSOH. What is the net ionic reaction between them? Okay, so starting from that, if no reaction occurs, write no reaction. No. Okay. So all of these are assumed aqueous at the initial point. If they're not aqueous, we've got a problem. That's ClO4, CSOH. All of these will be double displacement reactions. So I'm going to break it down from cation, anion, and swap them around. So CS, ClO4, and HOH. Now, here's where you have to look up. You look up on the chart, you see anything in group 1 is always aqueous. And ClO4 is another one of those anions that is always aqueous. But anything in group 1 will always be aqueous. And HOH, that is water. That's going to be a liquid. So when it comes to writing the net ionic equation, anything that's aqueous gets split up, and anything that is a liquid or a solid stays together. Minus CS plus ClO4, 1 minus, and water. Now, anything that appears identical on left and right gets crossed out. ClO4, ClO4, CS, CS. So the net ionic reaction is just H plus, aqueous, OH minus, aqueous, goes to H2O, liquid. That's all we got. It's a standard strong acid, strong base situation. Now, the next one. Which of the following compounds would have more than one resonance structure? To have a resonance structure, typically you need lone pairs and double bonds. Anytime you can move around the double bonds into one more place, you could have a resonance structure. So let's put these guys. Now, a different resonance structure may end up giving you a different formal charge setup, but a different resonance structure will not change the overall electron geometry. Okay, I'm just drawing these out real quick. Then the last guy, I got it. Drawing them out. The last guy is a little bit harder, but it's doable. Okay, go into the document camera real quick. Document camera. So I've had to add in, oh, shoot, added too many lone pairs there. We see right here, we have nitrogen, double bond, nitrogen, bond. And we have, what is not shown in the original drawing was the lone pairs. Nitrogen should have 5 electrons, 1, 2, 3, 4, 5. Because it had a negative charge, it made it 6. But what this means is that I have lone pairs to move around. So to make a resonance structure, what I can do is I can take this lone pair, or I could take that lone pair, it doesn't really matter, and pull it into a triple bond. Now, because nitrogen had an octet, it doesn't want to make any more bonds. What's going to happen is this lone pair, this double bond is going to flip over here. So a resonance structure for that could be this. Actually 1, 2, 3. That's going to be 2 plus. No, that's still 1 plus. Sorry. And this guy is 2 minus. So instead of having -1, -1, we have -2. We've moved those around, the electrons, so they shifted over here. And I could draw another resonance structure that's just the opposite, where it's a triple bond there and a single bond there. But you notice this guy, 2 electron domains, is linear. This guy, 2 electron domains, still linear. The shape has not changed. The shape has not changed. It is still linear. We just moved a double bond, a lone pair into a secondary, into a pi bond, and kicked a lone pair out of a pi bond. The same thing true with ozone. I could take a lone pair here swing it down into a double bond, and because of that, kick a lone pair out. So my resonance structure would be still bent. It'd still be bent, but now my now my double bond is on the other side. Both of those are valid resonance structures of each other. And this guy, while there's no lone pairs to move around, we can move around any number of pi bonds. I could just as easily take this pi bond and move it there, causing that guy to shift up there, causing that guy to shift down there. Or this guy could shift over here, causing that guy to shift over here, causing that guy to shift there, there, there. There's many different orientations of this same structure. I could just do this. Or I could be looking at a structure like this. All these double bonds that are 2 atoms away from each other can be moved around. So this version, I've just changed the orientation on this end guy. And this one, I've actually just reversed the whole thing. The whole thing kind of got mirrored. But all these cases, the double bonds are able to move. If these had all been single bonds, it would have been no go. But the idea here is, if we imagine these guys are all SP2 hybridized. This guy's SP. These guys were hypothetically SP2. Or possibly even SP. These guys were SP2. The whole idea is that these guys had empty p orbitals that could be used. These guys had empty p orbitals that could be used, that we ended up that allows this to work. If it is fully hybridized with the SP3, it's not going to work at all. But these pi bonds and lone pairs are allowed to shift around. Okay. Going back to number 16. Okay. Zinc, nitrate, and potassium chloride. So we're writing this down. Zinc nitrate and potassium chloride. I'm going to, instead of showing this, first I'm going to, what are the products? So a double displacement is going to form potassium nitrate and zinc chloride. So ZnCl2. If you wanted to balance this, you would have to put a 2 in front of the KCl. But how to predict whether a reaction occurs? Well, we're going to go down to our little table that I'm going to provide for you. This is not quite the same table as I provide, but okay. Nitrate, zinc, aqueous. Potassium, aqueous. Now go down to chloride. Chloride, potassium chloride, aqueous. Zinc, also aqueous. So with that in mind, too far. With that in mind, what can we say about this reaction? What we say about this reaction is that if this is aqueous, and this is aqueous, and this is aqueous, and this is aqueous, when we break all these apart, everything will cancel out. There is no solid, there is no liquid, there is no gas, there is no driving force. If they all remain aqueous, there is no and all remain aqueous and they all remain identical. So you'd write a total ionic equation that would look like this. Goes to, it'd be K, well, so I'd have to balance that 2K plus, 2NO3 minus, Zn 2 plus, and 2Cl minus. So writing that down, you'd see here, well, zinc 2 plus aqueous is the same as zinc 2 plus aqueous. 2 nitrates are the same as 2 nitrates. 2 potassiums are the same as 2 potassiums. 2 chlorides are the same as 2 chlorides. Had zinc changed in oxidation state, had zinc formed a solid, had we formed some sort of chlorine gas, or even some sort of liquid, this would be a reaction. But in this case, no solid formed, no liquid formed, no gas formed, so no reaction actually happened. We say they swapped places, but in reality, they are still fully dissolved by water, floating around by themselves. Maybe they went and got near another atom, but they didn't stick around long enough to make any sort of lasting impact. So that case, that problem was no reaction. No reaction. So what is the electron geometry of Bf3? So Bf3, boron has 3 electrons. Fluorine each has 7 electrons. So when you draw this guy, you would put the boron in the center. You would put 3 bonds to fluorine. Now, please note, your Lewis structure doesn't have to be pretty. This is not how that actually looks. I'm putting my lone pairs. When we go to the electron geometry, we have to say how many electron domains are on the boron. Boron is the exception. It doesn't need 8. It would like to have 8, but it doesn't always get 8. But even if you did something crazy, like made a double bond, this would not change the electron geometry. The electron geometry would stay the same. Because how many things are coming off of boron? 1, 2, 3. 3 electron domains off of the center atom makes the overall shape trigonal planar. Trigonal planar. So you may want to draw it T-shaped, but it's only going to be trigonal planar. So draw valid Lewis structure. I may not have one like this on the test, but this is an organic compound. This is as hard as they go, maybe, with drawing Lewis structure, because we're not quite used to this so much. But let's write this down. CH, but one thing to remember is that more times than not, look to the how I've structured this to tell you where to go. Hydrogen can only make 1 bond. Carbon will typically make between 2 to 4 bonds. More often than not, 4 bonds. Nitrogen will typically make between 1 and 3 bonds. Nitrogens almost always have a lone pair, especially in these organic compounds. So with that in mind, let's break down what we're seeing here. What we're seeing here is CH3, 2, CH, and H2. So let's take the CH3 by themselves. CH3 by themselves. There are 2 CH3 chunks. Carbon wants to make 4 bonds. Since the 2 CH3s, we're going to say they're going to come and go to the same spot. Now, of this option, what is the next atom in there? C. Okay. If I had a choice C and H only wants to make 1 bond. Now, here's where most people get tripped. They might want to put H then N. But you got to remember, carbon almost always wants an octet. How do you give it an octet? You make 4 bonds. So instead of making C, H, then N, we want to put the H up here, then the N off the C. Now, here's our bond. Here's the NH2. And then finally, nitrogen is 1, 2, 3, 4, 5, 6. It's 2 electrons shy, but nitrogen should have 5 electrons. We have 1, 2, 3. There's 4, 5. There's our Lewis structure of CH32, CH, and H2. This structure is what's called isopropylamine. Isopropylamine. Not super hard, but it's maybe something we're not used to. I don't think I really have any of those on the test, but it's still a good thing to know. If you have to take organic, you will have to be able to draw structures like these. Okay, what is the formal charge on the chlorines and the oxygens in this following compound? Cl, I'm not going to switch to the dot cam, but let's think about this. Chlorine is group 7A. Oxygen is group 6A. So to calculate a formal charge, you count half the electrons in a bond and all of the lone pairs. And we compare those two numbers to the and we compare those numbers to the group number. So oxygen with group 6, we have to look at how many electrons are actually around the oxygen. Well, by lone pairs alone, you have 6 electrons. You also have 1 bond. So our valence electrons should be 6, but the electrons we see are 7. So when we say 6 minus 7, we would have a formal charge of -1. We have 1 more electron than we expect. Now, each oxygen is identical, and so each oxygen would have a formal charge of -1. Now, chlorine, as I said, is group 7. You see 4 bonds, 0 lone pairs to chlorine. So 4 bonds means 4 electrons. 7 minus 4 is +3. +3. So chlorine in this Lewis structure is +3. Each oxygen is -1. Now, while I do not ask this question, what is the overall net charge of the structure? +3, -1 4 times would be -1 total. Now, number 20 is we classify acid-base precipitation or redox. To do that one, don't forget acid-base is a proton donor, a hydrogen donor, and a hydroxide come together to form water and a salt. You need both to make it an acid base. Precipitation is a double displacement where a solid forms, where there was no solid before. And a redox is one where a oxidation state changes. An oxidation state changes. So the first one, H2O2 plus chloride, hydrogen peroxide plus chloride goes to water and hypochlorite. Don't let this one trick you. Water being formed does not make this an acid base. The easiest way to figure this out is you look at chloride as 1 minus. Hypochlorite, if oxygen is 2 minus, chlorine must be plus 1 to give you a net charge of -1. So 1 minus 2 is -1. So chlorine is going from -1 to +1, a change in charge of 2. However, if you recognize hydrogen peroxide as the one exception for the oxygen being either 2 minus or 0 rule, you would also go, oh, oxygen is -1 on that situation. So that one was redox. The second one, zinc sulfate plus 2 potassium hydroxide, a base, goes to zinc hydroxide and potassium sulfate. Don't let the presence of a base trick you. There is no acid in there. There's no acid in there. If you look on the chart, you'll see zinc hydroxide being a solid. So what happens is aqueous goes to solid and aqueous, making that a precipitation reaction. Number 3 is the first real acid base. Sodium hydroxide, phosphoric acid goes to water and sodium phosphate. Hydrogens get transferred to hydroxides, forming water. And the last one, a pretty obvious redox. Silver solid and chlorine gas goes to silver chloride. Silver is an element. Chlorine is an element. 0 to +1, 0 to -1. It's a clear change in oxidation state, so it's a redox reaction. NO3. This one you have to draw out, but what rule does NO3 break? So try to draw NO3 the best you can. No, not NO3 1 minus, not NO3 1 plus, but NO3. So to do this, you're going to calculate all of our electrons. So NO3, N has 5, oxygen has 6, 6 times 3 is 18, 18 plus 5 is 23. If anyone knows something about math, this is going to be a problem. That's already a dead giveaway. NO3. So we put N in the center, put an oxygen, put an oxygen. That knocks off 6. We're down to 17. Say we put in 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17. You use 17. We're going to take one of these electron pairs, give nitrogen an octet. What's the one problem? This oxygen, how I've drawn it, has 7 electrons, not 8. Having that odd number of electrons is our issue. An odd number of electrons is our issue in that because of this, odd number of electrons gives a radical on the one of the atoms. So if it was NO3 1 minus, then everything's good. Everything would have an octet. Now, anything that is row 3 or below could have an expanded octet. But nitrogen is not allowed to have an expanded octet, so it can't even be A. Okay. What is the molecular geometry of the selected atom? So this one is asking you to look at the structure from the perspective of each of these guys being a central atom. If you look at it from the perspective of carbon 1, how many electrons? I've conveniently included all lone pairs so as to not trip you up. I've often in the past not included lone pairs. So this one I try to make it easy. Carbon 1 has 1. Let's count them. 1, 2, 3, 4 things coming off of it. And so, and they're all bonds. There's no lone pairs. And so that's tetrahedral geometry. Carbon 2 is 1, 2, 3, and there are no lone pairs. So it would be trigonal planar. Oxygen, 1, 2, 3, 4. But 2 of them are bonds, 2 of them are lone pairs, meaning this would be bent. The electron geometry may be tetrahedral, but the molecular geometry is bent. So once again, the answer was tetrahedral, trigonal planar, bent. 3 more problems. We'll be done. Which element of the following compound reaction is being oxidized, losing electrons? So you got to look. In this case, we're going to treat all non-elemental hydrogens as +1, all non-elemental oxygens is -2. So oxygen is going from going from 0 to -2. Hydrogen is going from 1 to 1. And carbon must be going from -4 to +4. So the question here is, which element is being oxidized, thus losing its electrons? Now, here's a hint. More often than not, it's not oxygen. There's a reason it's called oxidation. What is oxidation? The root word is oxide. Because when most elements get oxidized, they gain an oxygen. So oxygen is the oxidation agent, but it's not the element that is being oxidized. In this case, carbon is the element that is being oxidized. But hydrogen is not changing. Which of the following compounds is polar? So once again, this is a case where you have to look at equal and opposite opposing forces. Whenever you have elements of symmetry, they cancel out. Let's start with this one. You may not be able to see it right now, but come to lab, make this structure, make the tetrahedral structure, and look, CF4. Each bond in itself is polar. However, because of the nature, I could rotate this structure so that this F goes to there, and this F goes to there, and this F goes to there. I could rotate the structure so this F goes there, and this F goes there, and that F goes there. All these Fs are essentially interchangeable, meaning if neither F is more important than the other, they all cancel out. This is a case where the electron geometry is the same as the molecular geometry, and all the atoms are the same. Thus, they cancel out. Same thing here. This is slightly different. PF3Cl2. There are differences in the chlorine and fluorine. However, this chlorine cancels out that chlorine. These 3 fluorines, while they look different, once again, this is the same generalized shape as a trigonal planar. you can rotate this so this F goes to there, this F goes to there, and this F goes to there. No F is more important than the other F, and they all cancel out. However, this structure, this fluorine is opposed by a chlorine. This fluorine is opposed by a chlorine, and this fluorine is opposed by a chlorine. So in this case, the atoms are not canceling each other out. Thus, structure 2 is polar. Finally, structure 1, this guy, this F cancels that F, but this F is opposite of an H. Because of that, this is polar because we have these forces are not the same. And the last one, net ionic reaction. I will not ask this of you, but this was another acid-base one that was a weak acid. A weak acid base. So despite being aqueous, and being pretty straightforward as it comes to double displacements, there was a trick here that lost some people some points. You would have H2O liquid, and you would have potassium acetate, C2H3O2. Despite being aqueous, when you came to write the total ionic, this guy stays together. Why does this guy stay together? Because this guy is what is called weak electrolyte. A weak electrolyte in that it didn't break apart very easily. And so the net ionic equation, we can only cancel out the potassiums. We couldn't cancel out the acetates because it was a weak electrolyte and stayed largely together. Once again, that is not something I'm going to ask of you on this test. Not going to ask you to write a net ionic with a weak electrolyte. But that was 25 questions of last year's test. So, that in mind, this test is 20 questions. It's 20 questions, mostly multiple choice. There might be a couple net ionic equation ones. There'll be a couple draw the Lewis structure ones. But for the most part, it will be multiple choice. There might be one balance the chemical equation problem. But so it's going to be similar in nature to this test. You'll need to be able to determine sigma and pi bonds, at least for one question. You'll need to be able to tell something about hybridization, be able to identify molecular and electronic geometries, be able to determine whether this is a combination, single displacement, double displacement, decomposition reaction, see if this is an acid-base precipitation or redox reaction. Similar things to that. Now, sorry that this was such a major disaster. However, that's what we got. I want to thank you for your time. And I'll speak to you again on Wednesday, starting chapter, I think 9. So yeah. So have a good day. I will see some of you in lab. See some of you to take the test.